This talk presents IIP, an Integratable TCP/IP stack. This work is done by Kenichi Yasukata from IIJ Research Laboratory. TCP/IP is a standardized protocol suite commonly used for communication in computer networks. TCP/IP stacks are typically software that implements procedures to comply with the TCP/IP standard. TCP/IP stacks have been typically maintained as part of OS kernels. However, people found that it is hard for TCP/IP stacks in legacy OS kernels to effectively utilize the benefits of high-speed NICs. To address this issue, research and industry communities have invented many performance-optimized TCP/IP stacks. Essentially, their performance is excellent. However, they have a downside. They often incur high integration complexity. On the other hand, there have been portability-aware TCP/IP stacks that allow for easy integration. However, they often lack the care for performance-critical factors and cannot achieve high performance. The problem we address in this work is that none of the previous TCP/IP stack implementations allow for easy integration and good performance simultaneously. As a result, developers who wish to integrate a high-performance TCP/IP stack to speed up their software have had limited and laborious options. For example, intensively modifying one of the existing TCP/IP stacks, building a new TCP/IP stack from scratch, accepting performance limitations of an applicable TCP/IP stack, or giving up the integration. To address this problem, in this work, we develop IIP, an integratable TCP/IP stack that allows for easy integration and good performance simultaneously. From here, we look through the issues of the existing TCP/IP stack implementations. Performance-optimized TCP/IP stacks usually have various functionalities, like this. The first issue of performance-optimized TCP/IP stacks is that they often introduce a lot of dependencies on other components. Let's say the I/O subsystem depends on library A, and library A depends on OSB version X. Here, we have an application program implemented by application developers. The developers wish to integrate this TCP/IP stack with their application. However, this application depends on library C, and library C depends on OSB version Y. Normally, two different versions of an OS cannot coexist on the same system. As a result, it is hard for the developers to use this TCP/IP stack for their application. As we see here, dependencies on other components often increase integration complexity and limit the applicable environments for a TCP/IP stack implementation. The second issue of performance-optimized TCP/IP stacks is functionality conflicts. There is a new OS specialized for performance. And, let's say we wish to use this TCP/IP component on this new OS. And let's suppose this TCP/IP component depends on its specific thread runtime. In this case, we need to port the thread runtime of the TCP/IP stack to the new OS. However, the new OS already has its own thread runtime, and two independent thread runtimes normally cannot coexist. Here we see a functionality conflict for the thread runtime. As a result, it is hard to use this TCP/IP component on this new OS. So, functionality conflicts increase integration complexity. The third issue of performance-optimized TCP/IP stacks is limited choices for CPU core assignment models. Performance-optimized TCP/IP stacks often maintain threads for executing TCP/IP processing. And they also often assume application logic implemented by developers is executed by another thread. We can think of three potential CPU core assignment models for the threads executing application and networking logic. The first model, which we call split, runs the threads for application and networking logic on different CPU cores. The second model, which we call merge, runs the threads for application and networking logic on the same CPU core and duplicates the same setup to available CPU cores. In the third model, which we call unified, a single thread executes both application and networking logic, and the same setup is duplicated to available CPU cores. The point is that each of them has different performance characteristics. One of them is CPU utilization. In the split model, a busy thread cannot use other CPU cores' unused cycles. Consequently, the CPU utilization of a system adopting the split model tends to be low. On the other hand, the other two cases can fully use the CPU cycles. Another point with the CPU core assignment pattern is the cost of transition between application and networking logic. In the merge model, thread switching is necessary for every transition, and this operation is costly because it includes scheduling in the kernel. On the contrary, the other two cases are free from this cost. The issue is that many performance-optimized TCP/IP stacks often include the CPU core assignment model selection, and developers cannot choose a desired assignment model, although it is an important performance factor. This makes it hard for developers to build performance-optimal systems. From here, we briefly look into the issues of portability-aware TCP/IP stacks. One of the main approaches of portability-aware TCP/IP stacks to achieving good portability is to maintain limited functionalities and assume platform-dependent components are provided by developers. This design allows portability-aware TCP/IP stacks to be free from the issues that increase integration complexity. However, existing portability-aware TCP/IP stacks are not sufficiently aware of performance-critical factors. Specifically, they are often unaware of NIC offloading features, lack zero-copy I/O capability, and lack multi-core scalability. Consequently, existing portability-aware TCP/IP stacks cannot achieve good performance for various workloads. Okay, these are the issues of the existing TCP/IP stack implementations. Now we present the design overview of our proposal, IIP. To minimize integration complexity, IIP only implements TCP/IP processing functionality to reduce the chance of causing functionality conflicts. And IIP does not depend on specific CPU architectures, NIC, OS, libraries, and compilers. IIP is implemented in the C programming language, and its codebase is C89 and C++98 compliant, so that it can be easily compiled by old and future compilers. IIP assumes platform-dependent functionalities are provided by developers through its API. To achieve good performance, IIP pays attention to performance-critical factors that existing portability-aware TCP/IP stacks are not fully aware of. Specifically, IIP leverages common NIC hardware offloading features if available, supports zero-copy I/O, and adopts a previously proposed technique to enhance multi-core scalability. For more details on the design and implementation, please refer to the paper. From here, we present the performance numbers of IIP. First, we look into a workload that exchanges small messages. We use two physical machines and run a TCP ping-pong workload that exchanges 1-byte payloads. The pinger and ponger applications use IIP and user space for TCP/IP processing and leverage DPDK for packet I/O. We measure the throughput while changing the number of CPU cores from 1 to 32 on the ponger side, and the pinger side always uses 32 CPU cores. This graph shows the results. The x-axis shows the number of ponger's CPU cores. The y-axis is the observed throughput. The first performance factor we find from this result is multi-core scalability. In the few CPU core cases, we can see the performance of TCP/IP stacks which are unaware of multi-core scalability. As we see here, multi-core scalability is important to achieve high performance for workloads that exchange small messages. Let's look into a bit more details. In this graph, the default case activates all common NIC hardware offloading features and zero-copy transmission. And when we disable the checksum offloading feature of the NIC, the throughput is degraded. So, the checksum offloading feature is also the performance factor for this workload. Interestingly, when we disable the zero-copy transmission capability, we observe higher throughput. We find that for small messages, copying is faster than zero-copy transmission. Let's move on to the investigation on the effect of the CPU core assignment models. The experiment setup is mostly the same as the previous one. But we applied the 3 CPU core assignment models using 2 CPU cores on the ponger side. This graph shows the results. the x-axis shows the throughput, and the y-axis shows the observed latency. This line is the result of the split model, and this is for the merge model. The split model achieves generally lower latency compared to the merge model, and this gap comes from the cost of the transition between application and networking logic in the merge model. However, the merge model exhibits higher throughput than the split model, and we consider that this happens because of the low CPU utilization issue of the split model. On the other hand, the unified model achieves the best performance because it is free from the issues of the split and merge models. Here, we confirm the CPU core assignment model is important to achieve optimal performance. At last, we report the bulk data transfer performance. In this experiment, one machine runs a sender application and the other runs a receiver application, and the sender repeatedly sends the same data to the receiver. Both the sender and receiver use a single CPU core and perform the data transfer over a single TCP connection. The results are shown in this graph. The x-axis shows the size of the data that is repeatedly sent by the sender. The y-axis is the observed throughput. In this graph, the default case activates all common NIC hardware offloading features and the zero-copy transmission capability on both the sender and receiver sides. We find when the sender deactivates the zero-copy transmission capability, the throughput is degraded according to the size of the data. We consider this happens because the payload occupies the CPU cache. Here we see that zero-copy I/O is important for bulk data transfer. When the sender deactivates TSO, the throughput is almost halved. So, TSO is also a significant performance factor. And when the sender deactivates TSO and checksum offloading, the throughput goes down to around 10% of the default case. When the receiver deactivates checksum offloading, we see a similar trend. The throughput goes down to around 10%. Here, we find checksum offloading is very important for bulk data transfer. We observe that when the receiver disables LRO, it can still catch up with the link speed. We note that this does not mean LRO is not necessary, just we did not see differences in this workload. Here, we have confirmed NIC offloading features are indispensable to achieve high performance in bulk data transfer workloads. Okay, we have presented IIP, an integratable TCP IP stack that aims to allow for easy integration and good performance simultaneously. The source code is available at the link at the bottom of the slides. Please try it if you are interested. Thank you for your listening.